Hello students, in today's class we will learn about phase transformations, which is when heat is supplied to a substance, how it gets converted from solid to liquid or liquid to gas. So, those phase transformations, clear. So, to understand that we will be defining a term here called specific latent heat. So, you all know whenever you look at this term specific, we should understand that it is defined per unit mass, correct. So, this is also something which is defined per unit mass. So, I will first write down the definition for this. So, we can define specific latent heat as the amount of energy or you can say heat that should be supplied, or removed as well to change the phase of a unit mass of a substance, at constant temperature. So, this last point is very important. So, at constant temperature, we should not change the temperature, we should just change the phase, clear. For example, if I have solid, let us consider ice. So, if I have to convert ice into water, so I should not increase the temperature during that process, clear. So, if you have ice at 0 degrees, then you are going to convert that into water at 0 degrees. So, if you consider that scenario, so the amount of heat that is required to make that conversion is what we call as specific latent heat, if I consider a unit mass. So, in most cases, in most books and most of the questions which would be asked to you, they will be referring to this specific latent heat as latent heat itself. So, they will not be calling it as specific latent heat. So, they will be calling it just as latent heat, clear. So, even I will be calling it as latent heat, but remember that it is actually specific latent heat, which basically means it is defined per unit mass. So, based on that idea, we can actually write an expression for this. We can define latent heat, which is L, in this manner. So, L is equal to Q by M, clear. So, heat required to convert unit mass. So, that is what we call as latent heat. So, in this case you can see, if I have to write the units of this latent heat, you can easily understand. Q is basically in calories, you can also write it in joules. Mass is either in grams or kg. So, I can write the units for this particular latent heat as either calorie per gram or joule per kg. So, you can use any of these units. So, whenever you look at this, you should understand that we are talking about specific latent heat, even though they will be calling it as latent heat. So, it actually refers to per unit mass, clear. So, that is the basic idea. So, the heat that is required, so it can be either supplied or removed. The idea is something like this. For example, let us say we have solid and I need to convert that into liquid, clear. So, if I have to convert solid into liquid, heat is supplied, clear. Similarly, if I have to convert liquid into solid, so if I have to convert water into ice, I will have to remove heat, clear. So, in this case heat is removed. See, the idea is very simple. I have told you earlier also that there will be intermolecular forces between the molecules, and in solids the intermolecular forces will be stronger because they are very close. So, to convert that into a liquid, I will have to separate the molecules to farther distances, correct. So, which means I will have to spend some energy and then separate them. So, in that separation process, I am supplying the energy. So, that is why to convert solid into liquid, I need to supply heat, and if I remove the same amount of heat from liquid, I can convert that into solid, clear. So, this is the basic idea. This can also work with liquid to gas also the same way. If I need to convert liquid into gas, heat is supplied and if I have to convert gas into liquid, heat is removed, right. So, that is the basic idea. So, based on which process we are talking about, either solid to liquid or liquid to gas, we have different types of latent heat which we will be discussing about. So, let us see that now. So, the first one is basically called latent heat of fusion, latent heat of fusion. So, it is represented with L subscript F. Now, so let us understand what fusion means. So, to explain that, I will consider let us say ice. So, let us say we have ice here, and let us consider that this is 1 gram, clear, and this is at 0 degree Celsius. Now, if I have to convert this 1 gram of ice, let us say, into water. So, what we have here is water, and this is also 1 gram. So, when I am converting that, the same mass will remain, right, and I am not even changing the temperature. So, I am just converting the phase, but not increasing the temperature. So, in this case, so to make this process happen, so conversion of ice into water, we call this process as melting. So, you all know this. So, solid converting into liquid is called melting, clear. In the same way, the reverse of that, liquid converting into solid is what we call as fusion. So, fusion means that basically, clear. So, fusion means liquid converting into solid. Now, as I told you, we can understand latent heat of fusion just like how we defined it generally. So, in this general case scenario, we defined it as heat supplied or removed to change the phase of unit mass of a substance. So, same will be the definition for latent heat, but here we can write it as heat required for 1 gram of a substance to convert it from solid to liquid, clear. So, if I give this much amount of heat to ice, 1 gram of ice, I can convert that into 1 gram of water, or if I remove this much amount of heat from water, then I can convert it into ice. So, it works both ways. So, if I supply, solid to liquid will happen. If I remove heat, liquid to solid conversion will happen, and the amount of heat required for 1 gram is what we call as latent heat of fusion, clear. And just like we have discussed earlier, its units would be calorie per gram or joule per kg. Now, similarly, we also have one more phase change, correct. So, let us see the expression for that as well. It is called latent heat of vaporization. Okay. So, latent heat of vaporization is represented with LV, subscript V. So, in this case what happens? So, we will have water converting into vapor, right. So, if I consider, let us say 1 gram of water. So, if this is 1 gram of water, let us say this is at 100 degree Celsius, right. So, if this converts into vapor, so to represent vapor I will just show you molecules, right. So, this is vapor state, right. So, to make this conversion happen, the amount of heat that is to be supplied for 1 gram of water is what we call as latent heat of vaporization. So, this process you all know that it is called as boiling, and the reverse of this, vapor converting into liquid, we call this as condensation. So, once again, latent heat of vaporization also works both ways. We can understand it as heat that should be supplied to water 1 gram to convert into vapor, or heat that should be removed from 1 gram of vapor to convert that into liquid, which is water in this scenario. So, that is the basic idea. So, the definition is once again the same. The only thing is that we will have liquid to vapor in this particular scenario. Now, there are few values which I will be giving you, which will be quite frequently using in this particular topic. So, we can say that latent heat of fusion for the ice water transition is equal to 80 calorie per gram, clear, which means for every gram of water of ice to get converted into water, I need to supply 80 calories. So, 80 calories per gram, clear. Similarly, the latent heat of vaporization for water into vapor. So, we can say that this value will be equal to 540 calorie per gram. So, once again the same meaning. So, to convert 1 gram of water into 1 gram of water vapor, then I would require 540 calories. So, that is the meaning of that. Now, keep in mind there is one important thing. So, this phase transformation or ice getting converted into water or water getting converted into vapor. So, this happens at specific temperatures. You can't do this at any random temperature. So, they happen at specific temperature, and you know that you would have heard of this term. This happens at melting point, and this happens at boiling point. Clear? And whenever you see that there are two different phases coexisting together, for example, if ice and water are coexisting together at same temperature, then that temperature has to be melting point temperature. What I am trying to say is ice can be at 0, water can also be at 0, and in the same manner if water and vapor are coexisting together, then that has to be 100 degrees Celsius, which is boiling point. So, you can consider boiling point as the temperature where liquid and gas can exist together. By together, I mean in equilibrium, having same temperature. You know what thermal equilibrium means already. So, both water and water vapor can together exist in different phases at the same temperature, and that would be boiling point. And similarly, melting point means ice and water coexisting together. Clear? So, students, now we will see some questions based on latent heat. So, here you can see they are asking us to find the heat supplied to convert 20 grams of ice at minus 20 degrees Celsius to water at 25 degrees Celsius. Clear? So, which means, so I will have to start off with ice, which is at 20 degrees Celsius, sorry, minus 20 degrees Celsius, and I will have to finally get water at 25 degrees Celsius. Clear? So, this is what they are asking us to do. So, now we know that we can't directly do this transformation. We know that ice to water conversion can't happen randomly at any temperature, right. It has to happen at melting point, which is 0 degrees Celsius. So, which means I will have to first take this ice, which is at minus 20 degrees Celsius, to ice at 0 degrees Celsius. Clear? So, I will have to first convert this into ice at 0 degrees Celsius. Clear? So, this is what we will have to do in this particular scenario, and now I can make the phase transformation process. So, remember, ice to water conversion only happens at 0 degrees Celsius. Clear? So, in this particular scenario, now that I have brought ice to 0 degrees Celsius, I can now convert that ice at 0 into water at 0 degrees Celsius. Clear? Now, I have water at 0, I need to take, and the final result I need here is water at 25 degrees Celsius, which means I will have to further convert this from water at 0 to water at 25. So, these are the steps that are basically involved in the given conversion. So, first I will have to increase the temperature of ice, convert ice into water, then increase the temperature of water. So, this is a three step process. So, let us find the heat required in each and every step. So, this is step 1, this is step 2 and this is step 3. So, in step 1, so step 1 is just increasing the temperature of ice, right. So, the specific heat capacity of ice is basically 0.5 calorie per gram per degree Celsius. We all know the specific heat capacity of water, right. Okay. So, this is half of that. Ice has half the specific heat capacity of water. Okay. So, step 1 is to increase the temperature of ice. So, we know that for increasing temperature we will have to use Q is equal to ms delta T. So, m is 20 grams, S is 0.5 which is 1 by 2 clear into delta T. Delta T is how much? Minus 20 to 0, which means 0 minus minus 20. So, which will be 20. So, this is what I get, and solving this I will be getting 100 calories, clear. So, I have substituted everything in calorie per gram per degree Celsius, even this is in grams. So, the units gets cancelled and eventually I will have calories. So, anyways, so for the first step I need 100 calories. Now, step 2. So, in step 2 if you observe, this is just phase transformation. I am not changing the temperature here, just converting the phase, and you know whenever we need to convert the phase we will have to use which expression? Q is equal to ml or mlf, clear. And we have just earlier discussed that latent heat of fusion for ice will be 80 calorie per gram. So, I will use this result. So, when I substitute that I would be getting the mass is 20 grams into latent heat of fusion is 80. So, into 80. So, solving this will give me 1600 calories. So, for step 2 the phase transformation I need 1600 calories of heat. Now, let us look at the third step. So, step 3. So, for step 3 once again this is increasing the temperature of water, right. So, if I have to increase the temperature of water I need specific heat capacity of water. I will be using Q is equal to ms delta T once again, but this time I will have to use specific heat capacity of water. So, the mass is once again 20 grams. Remember that during this any of these steps the mass is not going to change, correct. Either temperature rises or phase changes, but mass remains same. So, 20 grams into, you all know the specific heat capacity of water is 1 into delta T. How much is delta T here? 0 to 25. So, which means change is 25. So, this is the expression which we would be getting, and when I simplify this 25 into 20 is 500 calories, right. So, that is the expression which I would be getting. Now, adding these the heat required in all these 3 steps will give me the net heat supplied in that process, and how much is that? So, here we have, okay, this is 200, right. So, this is 200 calories, 20 into half into 20 is 200. So, 200 plus 1600 plus 500. So, which is in total 2300 calories, right. So, that is the total heat required to make this process happen. Okay. Now, we will see next question here. So, they have given that 10 grams of ice at minus 10 degrees Celsius is added to 90 grams of water at 50 degrees Celsius. So, find the final temperature of the mixture, and it is also given in the question that all the ice has melted, right. Okay. So, let us first understand the components in this particular system given to us. We have 10 grams of ice and we have 90 grams of water at 50 degrees Celsius. And this is at minus 10 degrees Celsius, correct. Okay. So, now when both are mixed together, they have given that all the ice has melted, which means this will decrease its temperature, it gives heat, it loses heat, and this takes heat, rises its temperature, and they, because they told that all ice has melted, can I say that the final composition which I would get here, somewhere over here, will all the ice would have melted and become water, and water would have decreased its temperature and it would still remain as water, because in thermal equilibrium both should have same temperature, clear. So, I can definitely say that in this case the whole system finally will be water at some unknown temperature, some unknown temperature. And how much water would we have finally? This 10 grams of ice would get converted into water, and 90 grams of water would decrease its temperature and become water, and in total it would be 100 grams of water. What we have to understand here is, whatever is the heat lost by this much amount of water to reach this particular state is taken by this much amount of ice to reach this state. So, that is the equation we write, and let us write the principle of calorimetry. So, let me write heat gain first, and remember this has many steps involved in it. We have discussed earlier 10 grams of ice at minus 10 to this, you can consider this 100 as 10 plus 90, correct. So, I have to convert 10 grams of ice at minus 10 to water. Ice at minus 10 should be first converted into ice at 0 degree Celsius, and then this should be change its phase to water at 0 degree Celsius, and finally this should be converted into water at T degree Celsius, right. So, this is the process which should be followed. So, let me write the heats required for each and every step here. So, for this step, this is just rising the temperature of ice. So, I can write Ms delta T, M is 10, S is half, and delta T temperature change from minus 10 to 0, so which means 10 degree Celsius. So, into 10, right, plus. So, this step is just phase change. So, which means M into L can be used. So, M is 10 and L is 80. So, we know this value already. So, this is the second step, and for the third step, which is just conversion of water from 0 degree Celsius to T degree Celsius. I can write Ms delta T once again. So, M is 10, S is 1, and delta T is T minus 0, which is T. So, this is what happens. So, let us calculate the values. This is 100 by 2, 50, 800 plus 10 T. So, which is basically 850 plus 10 T, correct. Okay. Now, we have to bring 90 grams of water at 50 degree Celsius to 90 grams of water at some unknown T temperature. So, in this process we will have to remove heat. So, I will directly write the expression for removed heat now. So, this is supplied heat, right. So, this is for supplied, or we can say heat gained. So, this is heat gained and this is heat lost. Okay. So, heat lost by that water can be once again directly written as Ms delta T. M is 90, right, S is 1 for water, and delta T. So, from 50 its temperature drops down to T, which means 50 minus T. So, into 50 minus T. So, this is what we get, and solving this 90 into 50 will be 4500 minus 90 T. So, now according to principle of calorimetry, we can say that the heat gained by the substance in that system should be equal to heat lost by the system, I mean substances in that system. So, we can equate these two, and when I equate, I would be getting 4500 minus 850 is equal to 90 T plus 10 T, which is 100 T, clear. So, what is this value? This is 3650, right. So, I will be getting finally the value of T as 3650 by 100, which is 36.5 degree Celsius. So, that should be the final answer. So, that is the method we will be following. So, just look at which is losing heat, which is gaining heat, and then equate both, right. So, students, let us now understand something called as phase change diagram, right. So, a graph which represents different phases and conversion from one phase to other phase. So, what I am going to draw now is for ice, water and water vapor change transformation. Okay, so, let me call it as phase change graph. Okay, so it would be something like this. So, on the y axis we will have temperature, on the x axis we will have the heat Q. Okay. So, basically what we will do here is we will take, let us say, a container. We have a container in which initially there is ice cubes are present in that container, and we have placed a thermometer in that in this manner. So, there is a thermometer. Okay. And we are measuring the temperature basically, and here we are continuously supplying heat. So, let us say we have a heater as well, which is continuously supplying heat. So, now what we are going to plot here is the graph between the temperature recorded in this particular thermometer and the heat which is being supplied. So, we will look at how much heat is supplied and we will look at temperature. So, these are the two readings which we are going to take. So, this heater will give us the amount of heat supplied. So, Q supplied can be known by the heater, and the temperature of the system can be known by the thermometer. Clear? So, let us consider that just for an initial state, let us say that the initial temperature is some minus 10 degree Celsius. Let us just consider a scenario, or let us take a general value and call it as some minus T0 degree Celsius, because ice will be at negative temperature, right. Okay. So, let us say this is where ice was initially at minus T0 degree Celsius. Now, what we can say is that as heat is being supplied, so as I supply heat continuously, we can say that the temperature of ice will increase. That is what happens when ice is given heat, the temperature of ice increases. Will it be increasing continuously throughout the process? No, it will reach up to 0 degree Celsius, and once ice has reached 0 degree Celsius and if you further give heat to ice, what is going to happen? That is when phase change occurs. You can't continuously take ice temperature to, let us say, 10 degrees Celsius. You can't continuously give heat and take ice to more than 0 degree Celsius, correct? It rises up to 0 degree Celsius and then it changes its phase. So, I will directly plot the graph now. I am not going to write the equations for now. We can discuss that later on, how the shapes of the curve would come. We will be deriving the equations for that also. So, for now I will directly draw the graph and explain you how that graph is coming. Clear? So, the graph would be something like this. So, first, as the value of Q is increasing, temperature of the system also is increasing. So, that is what you see in the graph. So, as Q increases, T also increases. But after reaching this temperature, which is 0 degree Celsius, so after reaching this temperature, what will be observed was, even if Q increases, the the temperature does not change. So, the graph would be something like this. You will understand that in a while. Now, after some time, after some more heat being supplied, what happens is we will once again observe the temperature being raised. So, this time we will observe that the temperature is once again raised and it would be something like this. So, once again as Q is increased, temperature will also increase. Now, if I continuously supply heat, so once again after some particular value, we will observe that the graph becomes horizontal. So, this is something that happens during this process, right. So, let us consider this as a closed container. no mass is being left, I mean no mass is leaving the system. Okay. So, this is how the graph looks like. Now, let us understand what is happening. Why is temperature rising here? Why is temperature not rising here? And once again, why is it rising? So, what happens here? I have told you earlier that this is the process which represents increase in temperature of ice. So, as I supply heat, the temperature of ice is rising. So, that is what we look at in this graph. Now, once we reach this state, why is the temperature of the system not rising? Now, you know the answer for this. Because the temperature has reached 0 degree Celsius, ice will not increase its temperature. By taking the heat, now ice gets converted into water. That is the reason why even though I am supplying the heat, there is no rise in the temperature. The temperature remains at 0 degree Celsius. Clear? So, what happens here is, let us say I have started with some 50 grams of ice, just to understand. Clear? So, the 50 grams of ice, as I supply the heat, by the time it reaches here, that would reach a temperature of 0 degree Celsius. Clear? Okay. Now, what happens here is, as I supply the heat, now slowly the ice starts melting. So, after this much heat, 1 gram of ice will melt. After this much heat, 2 grams of ice will melt. So, in the same manner, we can say that after this much heat, this much value of heat is supplied, we can say that all the ice will melt. Clear? So, what is happening here in this region is ice is melting into water. Clear? And what has happened here? What is the role of this point here? I mean, what is the significance of that point? So, this is where all ice has melted. All ice in the system has melted. Now, when all the ice in the system has melted, and if I am further supplying the heat, what is going to happen? Now, it has everything has become water, and now I am giving heat. So, what happens? The temperature of water rises, and that is what you see here. Clear? So, this is the region which represents increase in temperature of water. Clear? Okay. Now, what is happening here once again? Why is the graph becoming horizontal once again? Now, you can easily guess that, because here we can say that the water would have reached a temperature of some 100 degrees Celsius, which is the boiling point, and once we reach that particular temperature, the water temperature cannot rise further. The water has to change its phase into gas, into water vapor, correct? So, that is what happens there. So, this is the region which represents water boiling into vapor. So, that is what each and every part of the graph here represents. So, whenever we get a straight line with some slope, it represents the rise in temperature. Whenever we get a horizontal line which without any rise in temperature, that represents either a melting process or a boiling process. So, here we can say that this one signifies melting and this one signifies boiling. Clear? So, like I told you, once we understand how these lines are drawn, I mean what will be the slope of this line, what will be the width of this line and slope of this line. So, we can also solve some numericals based on that. So, we can do that in the usual class discussion. Clear? So, for now just understanding this graph and why these lines are being formed like this is enough for us. Clear? So, as I told you, we can make one more analysis here. You can guess this easily. If I give the values, you know that specific heat of ice is 0.5 calorie per gram per degree Celsius, correct? And specific heat of water is 1 calorie per gram per degree Celsius. Now, I have told you in the first class, higher value of S means what? It means it is difficult to change its temperature, correct? So, That is the reason why if you look at this graph, this is the graph for increasing the temperature of ice and this is the graph for increasing the temperature of water. You would observe that in the case of ice, the graph is more vertical, and in the case of water, the graph is more horizontal. So, this is having more slope, whereas this is having less slope. What does that mean? It means that even if I give this much amount of heat, let us say this much amount of heat, I can rise this much amount of temperature for ice, whereas here if you see, I have to give this much amount of heat to rise this much amount of temperature. So, from the graph I think you can understand that the rise in temperature is almost same for ice and water, but if you look at the heat supplied in the case of ice is lesser and heat supplied in the case of water is larger, and the reason for that is this: ice has less specific heat capacity and water has high specific heat capacity. So, to change the temperature of water, I need to give more heat. So, that is what we see in this graph being more horizontal. Clear? So, lesser slope means more specific heat capacity. So, these are some ideas which we will have to get from this graph. So, like I told you, we will do a detailed analysis and solve numericals based on this later on. Clear?